Hi, this is Dr. Stephen Jones, and this is part 2 of project management. You will notice that project management probably uses the least amount of math compared to several other chapters that we found in the text. And what math there is largely algebra, but that's okay. It's because it's a different type of control system than you would find with, say, linear regression or with something else out there. Okay, so sensitivity analysis in project management, why would you even be concerned about that? Well, because remember at the end of the last lecture, we were looking at, is there a possibility for you to delay certain weeks? Why would you do that? Well, perhaps there's a delay in labor, like a strike, or like key craftspeople who are unable to show up, or perhaps materials have not arrived to be able to start a different activity. And what you want to know is which activities, if there's any delay at all, are going to begin to delay the entire project, because you don't want to do that if at all possible. You want to keep the project on path. So you take a look at that and look for predecessor and successor activities, and then also parallel activities. And you remember those looking at the graphic representations. A was a predecessor to C. C is a successor to A in this Foundry project that we were looking at. And A and B were parallel activities in that they both could occur at the same time, and you might be able to increase or decrease when the start times were for B or D and still not affect the overall project's time. Now, PERT itself, as we looked at, PERT itself doesn't look at budgets or costs, and so a variation of this actually does have a way for us to monitor the progress of a project with an intent to create a budget that'll help us to know, are we overspending or underspending based upon how much has gotten spent up to this point. Now, part of this is obviously simply looking at the amount of time we're spending on it, as opposed to increases in fuel or in increases in materials costs or labor costs, etc. But this does allow us to see, are there areas that we can, well, as we will take a look at, areas that you can crash or reduce times on. While that increases the budget, it may decrease in terms of, if you're going to reduce the size of the number of weeks that it takes to complete a project, you may actually save money in other areas, and it pays for itself. Or it could be more expensive. It all depends on what the critical resources are for that activity. So, if we're going to do this, the first thing that you have to do is identify all your costs for any one of those activities. And if it's a large project, you're probably going to have several interconnected activities and objectives out there. You can then convert that cost for an activity into a cost per week, because you can simply divide the cost by the number of weeks. So if it's 24,000, or in this case they show 48,000, and it's a 4-week activity, then you budget $12,000 per week for 4 weeks. Now, that doesn't mean you're actually spending $12,000 a week, or that you should expect the actual number of dollars being spent to be 12,000 evenly throughout the whole process. It is quite possible you have to spend more at the start or at the end of an activity, but it's a budgeting process. So it's an attempt to try to see over, say, 10 or 15 or 50 weeks, if you're staying within budget limitations. And earliest and latest start times should be able to help you understand when you're going to need the cash to be able to take care of each of those activities. So in this situation here, looking at a Gantt chart, which is a graphical representation of when certain activities start and when they're expected to end. And in this case, I've seen Gantt charts on walls before at some companies. It just shows you when certain things need to occur, and you can move, as we were looking at it before, you could move F a little bit later so it shows up here, and it doesn't affect the end time of 15 weeks. So you have the ability to move some things back and forth, and you graphically represent it this way. So now we create a table that does just what we were looking at and how much the cost would be on a per week basis. And by doing that, you can then look at the amount of budget that you're spending on each week. So in the first week, if you started everything off in the first week, you would expect then to spend $21,000 for week 1, because it's going to be $11,000 for each week of A and $10,000 for each week of B. And B starts here, so it would go all the way down. But remember, B does have the ability to wait a week to start if you wanted to, and so if you needed to do that, then it would shift your budget outlays that way. And we see that with this table, where now the numbers change a little bit. The first week's outlays are less, and later weeks are a little bit more. And so taking those numbers and plotting those into essentially an XY graph, you have the ability to see where there's more give and take in a budget, and where costs could start to spiral out for you. And that helps you, one, if you're needing to go out and get bank financing, how long can you push that bank financing out before you actually have to take it, or how soon do you have to go get it before the whole project bogs down and puts the company way behind. Now, if you're monitoring then these project costs and you see that you're starting to go out of whack a little bit, perhaps you can shave a little bit from a different part of the budget to stay within line. And the reason you got to stay in budget is largely because you've contracted out there to another company to do something, and in this case, remember, we're doing air pollution control. They're wanting to make sure that they don't overspend for this project and have to spend too much for it if they don't have to, and they want to be sure that they get done as quickly as possible, because there are fines looming out there if they take too long on getting the project done. So if something is delayed out there, they might have to do what's called crashing in order to collapse the project down again. Or if you found yourself with the government moving a deadline on you, which happens periodically, just in the same way that a customer can change his or her mind and want something faster or later. But you would project crash when you need to collapse the objective's time period, either because of delays in other activities or because of changes in deadlines by the customer, whoever that would be. Therefore, to do that, you would use that critical path and see where along the critical path you might collapse the timeline. And by collapsing that timeline, you may find that a different path now becomes a critical path. So if you were able to collapse B or D or F a little bit, you might find that a new critical path actually emerges out there. Or if you can crash something, if you can crash something on the critical path, then you might find that B and D and F now become on the critical path. Sorry about that. So let's take a look back at our example. General Foundry. Suppose that instead of the 14 weeks or 16 weeks, we're actually collapsed down to 12 weeks. So if it's a 15-week project, then how do we make that 12-week, new 12-week deadline so that we don't start incurring 3 weeks worth of fines or go to jail or lose a customer, something, whatever the reason that the collapse might have happened. And so you take a look at which activities could get crashed and what the cost for crashing would be. You notice that for A, you can crash it down to 1 week instead of 2, but it's going to cost you an extra $1,000 out there if you choose to do that. So you can graphically represent what those crash costs would be and the amount of time that you might be able to save yourself, and then start to look at which of these activities should we actually drop. Because while you might go in and say, well, it's easy, just drop drop B down 2 weeks and it's going to cost you $4,000. Well, at the point of crashing B, it's not on the critical path. And because it's not on the critical path, it does not actually shorten the activity time. It's got to be on the A, C, E, G, and H. So one or more of those have to get crashed. So perhaps crashing G from 5 down to 2 would shorten it by 3 weeks, and that would help get you to the 12 weeks. But would that be the most cost-effective way to do it? Just because it could shorten it down by 3 weeks, would that be the easy way to? Would that be easy, and would it be the most budget-wise way to reduce those costs? And so we would use potentially something along the lines of linear programming. Now you can use other methods. You could just look at it and calculate it for yourself. But if you use linear programming out there to try to do this, you then would have each activity that's in the system and put that out there as one of the variables, and then you would have constraints such as start times, finish times, weeks that an activity could be crashed, and weeks, costs, etc. So if you look at activity times here with the original numbers that were given to us, you then could you would be looking at the budget, you would then be looking at, let's go back to that. Yeah, that's the original graph that you have, and then putting the constraints in that you have from the problem as to how many weeks can be crashed on any one constraint, and looking at costs that occur in there. So while you have weeks here, and again G steps out as 3, but it also happens to be $2,000 for each week, or in other words, $6,000 total extra cost. Is there a way to get 3 weeks on a critical path that helps us to do that at the least cost? So if you could actually crash some of these things at 1 week or 2 weeks and do it at $1,000 a week, you'd save yourself $3,000 potentially. And then you still have to get down to 12 weeks. And so linear programming, you put your constraints in there just as we've done before in Excel. And notice how they set this process up in Excel so that you can see what each of the constraints would be, and you then create the same right hand and left hand sides that we did before, and it comes out that you can save $5,000, pardon me, that your cost is going to be $5,000 to crash the project by 3 weeks, and that's the best process that you can do. And you're going to do that by crashing G for 2 weeks, A for 1 week, and it's going to cost you $5,000, but that's the cheapest way to stay on the proper critical path. Anyway, so that's an option for you out there. We typically try to keep processes within budget and within time constraints, and PERT, CPM, and several methods here have relatively easily helped us to be able to look at how to maintain those controls.